Oasis Incubator Online. Title: A World of Cycles 1. Discovering Solutions to Intricate Problems. Welcome to A World of Cycles 1. In this video, we will explore the importance of recognizing and understanding cycles in our environment, highlighting how a holistic view can unveil solutions to complex challenges. This index presents the different topics that will be addressed in the presentation on mammoth population dynamics, from the introduction to the conclusion. Key aspects such as historical background, the basic structure of the model, and the effects of feedback loops on the mammoth population will be explored. Each section provides an overview of the main points to be discussed, allowing for easy navigation through the presented content. Objective. In this slide, we set our objective to explore the vitality of recognizing and understanding cycles in our world, as well as to highlight how a holistic view can unveil innovative solutions to complex challenges. In this introduction, we delve into the importance of recognizing and understanding cycles in our world, from the ancient extinction of the mammoth to the complex contemporary population dynamics. Welcome to the first model titled A World of Cycles 1, Discovering Solutions to Intricate Problems. In this simulation, we'll explore the factors contributing to the decline of the mammoth population and simulate the effects of human hunting on their numbers. Scientists have long debated the causes of mammoth extinction, ranging from climate change to human predation. In this model, we'll focus on the impact of human hunting as a significant factor. Students will construct a stock in flux map to visualize the dynamics of the mammoth population, incorporating reinforced and balancing feedback loops to understand the effects of birth and death rates. Additionally, a causal cycle diagram will illustrate the interconnected cause and effect cycles driving the survival of the species. Using simulation software like Stella and Simulate, students will experiment with different rates to simulate various scenarios and observe how the mammoth population changes over time. Finally, an interactive results presentation page will allow for easy manipulation of variables and sensitivity analysis to explore the consequences of different conditions on mammoth population dynamics. Join us as we delve into the complexities of mammoth extinction and uncover insights into the delicate balance of ecosystems. In this slide, we present the basic structure of the mammoth model. Observe the depiction of a bathtub symbolizing the system's capacity to contain the mammoth population, along with the flows of births and deaths. The schematic image of the bathtub illustrates how the model can represent any element, from mammoth populations to emotions and feelings. This visualization helps us understand the dynamics of the mammoth population and its interaction with the environment. In this slide, we observe the effect of the reinforced feedback loop on the mammoth population. When this cycle grows, the mammoth population also increases. This illustrates how factors that reinforce growth, such as increased resource availability or reduced threats, can have a significant impact on population size. It is crucial to understand how these loops can influence population dynamics and the management of species conservation, such as mammoths. In this slide, the effect of the balanced feedback loop on the mammoth population is demonstrated. When this cycle grows, the mammoth population decreases. This illustrates how factors that balance growth, such as resource scarcity or increased threats, can have a negative impact on population size. It is crucial to understand how these loops can influence population dynamics and the management of species conservation, such as mammoths. In this slide, two diagrams are presented to illustrate the population dynamics of the mammoth, the closed-loop diagram and the stock and flows diagram. The first one, known as a closed-loop diagram, is used to narratively explain the cycles of a system. Although it may not contain all the elements of the model, it is useful for providing a general understanding of the system's functioning and aiding in making informed decisions. On the other hand, the second diagram, The stock and flows diagram is more rigorous and shows all the components of the model. Although it may be harder to explain, it is used to simulate the impact of decisions over time and better understand the system's functioning. These results allow us to be better prepared to implement changes or intervene in reality. Determining the sign of a complete cycle is crucial in understanding its dynamics. Here's a refined explanation. In these diagrams, each complete cycle bears a sign, either positive or negative. Calculating this sign involves a detailed analysis of how each variable influences the others within the cycle. To illustrate, consider selecting a variable within the cycle and ask, if this variable increases, what happens to the next variable in the sequence? If it increases, assign a positive sign, plus, and if it decreases, assign a negative sign, dot. Proceed to the next variable in the sequence and repeat the process. Continue until you close the cycle. Then, count the negative signs, throughout the cycle. If the total count of negative signs is even, classify the entire cycle as positive or reinforced feedback. In the center of the cycle, name it with the letter R, followed by a number if needed when there are multiple cycles of this type. On the contrary, if it is odd, classify it as negative or balanced feedback. For this case, in the center of the cycle, annotate a letter B and a number if required. If there are no individual negative signs, the cycle is considered positive. Sometimes instead of the letter R, it is indicated with a plus sign, plus. This method ensures a comprehensive understanding of how variables interact within the system, allowing for informed decision-making and strategic interventions. In summary, these diagrams help us understand how different elements influence the mammoth population dynamics and how we can make informed decisions for their conservation. Now, we will delve into the model's dashboard. We will transition from the cause and effect cycle diagrams to the model itself to run simulations and observe the graphical results of the system's behavior. We will be able to appreciate what happens if the mammoth birth cycle, or positive cycle, is equal to the mammoth death cycle. Then, we will examine what occurs if the birth cycle is stronger than the death cycle, or vice versa. We will also explore the consequences when the mammoth death cycle outweighs the birth cycle. These simulations will allow us to understand how the system behaves under different conditions and the impact of variations in birth and death cycles on the mammoth population. In this slide, we observe what happens when the birth rate exceeds the death rate in the mammoth population. Clearly, it can be seen that the population grows exponentially. This phenomenon illustrates how an increase in birth rates can lead to rapid population growth if not counteracted by a balance in death rates. It is essential to understand how these changes in birth and death rates can influence population dynamics and species conservation planning, such as for mammoths. In this slide, we simulate the case where the death rate exceeds the birth rate in the mammoth population. In this scenario, the mammoth population declines, which may result from factors such as intensive mammoth hunting or the spread of diseases. This scenario demonstrates how an imbalance in birth and death rates can lead to a significant decrease in population. It is crucial to understand how these external factors can influence population dynamics and conservation strategies for species like mammoths. In this conclusion, we've explored how various factors influence the growth or decline of the mammoth population, from birth and death cycles to feedback loops. Each component is vital for understanding population dynamics. This understanding is essential for effective species conservation and management. By integrating this knowledge, we can move towards a more sustainable future for life on our planet. References. Connect with us. We are here for you. Thank you for your interest in Oasis Incubator Online. We are here to assist you with whatever you need. Feel free to reach out to us for more information, to answer your questions, or to discuss how we can collaborate. Here are our contact details.